Next up, we have John Schanck, who will be talking about revocation checking that works. Let's welcome John.
Thank you. So Josh showed that incredible chart from Let's Encrypt, 500 million certificates, valid certificates on the web at any given time. But Let's Encrypt is just one of 100, maybe a little more CAs. And collectively, those CAs have issued 1.1 billion certificates, not ever, but valid certificates at any given time. And in a system that large, you're going to make mistakes. The best CAs make mistakes and subscribers make mistakes. When that happens, you have to be able to revoke certificates. What you might have noticed in Josh's talk also is that he said that revocation mechanisms were janky. And that's the consensus opinion. It has been for as long as I've worked in cryptography. Revocation checking doesn't work. It's broken. So today I want to tell you about some of the work that we're doing at Mozilla to change that. Okay, so starting from where we're at today, there are two mechanisms that are in broad use. Okay, you have certificate revocation lists. These are authoritative lists of revoked certificates that are signed by the issuing authority. The downside to CRLs is that they're quite large. It's a few hundred megabytes if you want to get the complete collection of CRLs for the web PKI. Because clients can't download that much data and CAs don't want to serve it, for the most part, people rely on an online protocol, an online certificate status protocol, or OCSP. And this is a privacy leak. That's a big problem with it. It wasn't as big of a problem when we were not encrypting our DNS queries and when we were not encrypting client hellos, but it's more of a problem today. OCSP is also slow. You're gonna block your TLS connection while you go check with another server about the status of the certificate, and that's gonna take maybe hundreds of milliseconds. On top of that, the results are allowed to be up to a week out of date, according to the baseline requirements. So it's not clear that it's actually giving you good data. And now a more pressing concern is that it's optional to support. CAs no longer need to provide OCSP. And so there's really no future for this protocol. In response to that, people are trying to move to short validity periods, which is nice because it avoids the revocation problem in some sense, but there are a lot of open questions here, like how short of a validity period do you need before you can really do away with revocation? I'm not sure that I want a certificate around for 5 days after it's been compromised even. And Let's Encrypt might be able to move pretty quickly here, but the entire web PKI will take years to migrate to short validity certs. So the short validity certs are going to be part of the solution. Another part is going to be compact or summarized CRLs. So there are two ideas here, and there's a few different proposals for how to do this. Compact CRLs would be compressed representations of CRLs that can be delivered to end users and queried privately, just like CRLs could be in principle. And summarized CRLs would be, you take the list of CRLs and you remove some administrative revocations. Maybe you only publish the key compromise revocations. The pros and cons here will really depend on the mechanism that's chosen, but you're gonna wanna ask, like, can we really make these things small enough? Can we make them comprehensive enough? And what about, the additional trust assumptions that we're adding to the system by using these things? For Firefox, the fact that OCSP is going away is a bit of a problem because we use it right now. 18% of revocation checks are performed using synchronous OCSP. We also get some OCSP responses from TLS servers at staple OCSP at 27%. And then we cache both of these types of responses and we're able to use our cache 55% of the time. But that 18% is the real problem for us from a performance perspective, at least. The median request time is 113 milliseconds. So we would like to use something else, and the technology that we've chosen to move forward with is called CR-Lite. This comes from a 2017 paper by Larish, Chofnes, Levin, Maggs, Ms. Levin-Wilson that was presented at Oakland in 2017. The idea here is quite simple. It's a very elegant system. So you have one party that's going to play the role of an aggregator and try to get a global view of the web PKI. That aggregator is going to go and get a list of known certificates from certificate transparency logs, and then they're going to get a list of revoked certificates from CRLs. They're going to take all of the revoked certificates and put them in a Bloom filter. And if you know anything about Bloom filters, you know that they have one-sided error. So it's possible that you take a non-revoked certificate, query it against the Bloom filter, and it shows up as revoked. Okay, we don't want that. but we have the list of all known certificates. So we just enumerate all of the false positives and put them in another Bloom filter. Okay, and now, well, you have one-sided error again, but it's in the other direction. So you look at the revoked certificates and see if there are false positives in that collection, and you put those into another Bloom filter. And you keep doing that until you've eliminated all of the exceptions. You can then take that cascade of Bloom filters and ship it to users. Crucially, you have to include metadata about which certificates were known at aggregation time. So Mozilla took note of this and spun up infrastructure for it. And in 2020, we had an implementation and we were prepared to do a rollout. We halted that rollout in early 2021 when it was still in nightly because we found false positives. Sites that were not serving revoked certificates were coming up with revoked statuses. And we realized that it was because of the metadata that we had communicated about which certificates were known to the aggregator. So we fixed that in 2022. We had a revised implementation with better metadata, and we went through the full process of rolling this out to nightly and beta, and eventually to 1% of release users. And that's when we found out that it was going to be too expensive for us to run. At about the same time, in 2022, Mike Hamburg gave a nice talk at RWC with a proposal for doing something like CR-Lite, but with a different data structure at its core, so replacing the Bloom filters. And so in 2024, when I got some time, I redesigned our CR-Lite implementation around some of Mike's ideas. The news in 2025 is that we've shipped this. In the last 2 release cycles, we've done a gradual rollout, and there are now over 100 million users checking revocation statuses with CR-Lite. And it's the default revocation checking mechanism in Firefox 137. Okay, so the story of how we got here is largely the story of a new data structure that we're calling a club card. It's a membership test. That's where the name comes from. This will be presented at IEEE S&P later this year. So these Bloom filters had an inherent 70% overhead with respect to a natural lower bound for encoding a subset of a set. Mike's work improved this to 11% using what are called 2-level cascades of retrieval functions. That's a bit of a mouthful, especially when we start adding more adjectives for domain partitioning and things like that. So we call these things club cards. This domain partitioning is an idea I'll talk about more in a second, but the key point is that these lower bounds from previous work had been assuming that there was a uniform revocation rate across the entire web PKI, which is not the case. Different issuers have different revocation rates, and the revocation rates vary over time. And that variance in revocation rate can be exploited to give you better compression. So that's what we do with club cards. And I can show you what that looks like in practice. The green line here is the size of Bloom filter cascades that we were publishing late last year. And the blue line is the lower bound for an unpartitioned data set. And the fact that there's a downward trend here doesn't really matter, that we're really looking at the difference between the green and the blue lines. That's that 70% overhead that I was talking about. Here are the lower bounds if you partition the web PKI by issuer or by issuer and expiry. Orange is by issuer and red is by issuer and expiry. And then here are the club cards that we actually publish. So we're about 11% off of that issuer partitioned lower bound. And we have code to do the issuer and expiry partitioning as well from a Waterloo undergrad who interned with us last fall, Gavin Wang. So we'll roll that out eventually, and that line will drop further. That's if you want to compress full snapshots of the web PKI, but you don't actually want to do that every day. You also just want to publish delta updates. And so the green line here are the size of basically delta CRLs, just lists of issuer serial pairs at about 200 kilobytes. We can encode that same data using our club card data structure and cut it in half to about 100 kilobytes. And you'll notice here that we're still quite far off of the lower bound, that orange line. But that's really because of metadata overhead, and that metadata is compressible. So if we just apply gzip compression, which our CDN does for us, we drop down to about 50 kilobytes. And then if you have a client that already has yesterday's club card, they can use that with a dictionary compression scheme like zstandard or Brotli, and basically remove the overhead for future, remove the metadata overhead for future delta updates. So you do that and you drop down to 25, 30 kilobytes. So our current deployment, we're shipping all 4 million revocations that are in the WebPKI revocation set, which we gather from about 300 megabytes of CRLs. We encode those in a 4 megabyte snapshot every 45 days, and then we do delta updates at 12-hour intervals on top of that. And those delta updates are about 50 kilobytes using this dictionary compression idea. You can compare that with Chrome's CRL sets. They publish essentially all key compromise revocations as issuer serial pairs for about 500 kilobytes once a day. Okay, so we're publishing more than 100 times as many certificates at half the latency for a third the cost. Okay, and with CRLite enabled, we are servicing 95% of revocation checks with CRLite, and only falling back to OCSP for about 5%, 1% are synchronous OCSP requests. We have a plan for getting that 95% up. Largely, it means getting a more up-to-date view of the WebPKI. And as expected, we get an improvement in median TLS handshake time. So as our use of synchronous OCSP has dropped from 18% down to 1 or 2%, our median TLS handshake time has dropped by 30%. Actual impact on top-level page load metrics isn't that great. It's only a 1% improvement or so. TLS is not the most expensive thing that clients do, but it's an improvement nonetheless. Okay, so I called this talk toward revocation checking that works, and that kind of sounds like we have a revocation checking mechanism that works. So what do I mean? There are still 3 changes to the WebPKI that would help us make CRLite sustainable going forward into the future. The first is shortening validity periods, right? So this idea where we publish full snapshots and then delta updates works well enough, but we don't actually need the full snapshots. If you have, we don't actually need the full snapshots. We could just do delta updates, right? You can imagine that if you did delta updates for long enough, all of the certificates in that full snapshot would eventually expire, right? So we publish these full snapshots because they reduce the client-side computational costs of using the system, but we don't really like publishing them because they increase our bandwidth costs. If validity periods were 45 or 90 days, then we know that we could just completely get rid of the full snapshots and reduce our bandwidth costs by a factor of 2. The second thing we need to do is switch to the static CT API. There's 2 improvements that we'll get from that. One is there'll be less rate limiting on our requests, so we'll have a more up-to-date view of the WebPKI at any given time. And the second, more important change is that with a 0 or a very short merge delay, our aggregator will be able to claim that it has seen a higher percentage of the certificates that it's actually seen. And that will hopefully get that 95% coverage up to maybe 98% or higher. Okay, and then the third change that would help us is if we revise revocation reason codes a bit, drawing a clearer line between those reason codes that are security critical and those that are administrative. Thinking there being that maybe there are some revocations that we don't actually need to push to users. We could encourage subscribers to revoke with an administrative reason when they don't need the revocation to be visible to systems like CRLite. Okay, so I have a few more minutes, and I want to talk a little bit about this club card data structure in some more detail. The core technology here is something called a linear algebraic retrieval function. The idea is basically you have a vector valued hash function H, and then you can encode a bit of information B about a document by finding some vector X that has inner product B with H of the document, right? And you can encode one bit of information about many documents by just setting up a linear system like this and solving for X. Motivating use case here would be that B encodes membership in some set. And you can extend this to encode more than 1 bit of information to create a k-bit retrieval function just by adding more columns to the X and the B terms. The ideal case, you would have some minimal perfect hash function so that after row reduction, your system was diagonal, and you could just write down the values for the X terms. You're not going to have a minimal perfect hash function in practice here, but you can do pretty well by just making sure that that hash function has all of its coefficients in a narrow ribbon. So the matrix looks like this after row reduction. You can solve that very quickly, even when you have matrices that have 100 million rows, as we will. That idea almost works. You do need to have a little bit of extra space in there, some free variables to make sure that the system ends up being solvable. But putting all that together, there's something called a ribbon retrieval function. There's a nice literature on it, and here's some papers that you can look at to learn more. The other thing that we need is Mike Hamburg's two-level cascade construction from that RWC 2022 talk. The idea here is use two retrieval functions. The first one, you find some matrix X so that the hash of any revoked document times X comes up as the K bits of zeros. And that's going to give us factor 2 to the K suppression of false positives for things that are not in the set, right? You take a random value multiplied by X under some heuristics about what X looks like, you will not get 0. 1 minus 2 to the K, 2 to the minus K times. Once we have that X, we can enumerate all of the documents that do come up as 0. So just like we were doing in the Bloom filter case. So we'll have all of the revoked documents and some small fraction of the non-revoked documents. And then we just put those all into a second retrieval function. We solve for some Y. We have a different hash function, G. So we've solved for some Y, where G of any document times Y is equal to its actual revocation status. So it's either 0 if it's revoked or 1 if it's not. Okay. And one improvement that we've really made here is we have a new version of ribbon filters, which have a partition of the domain in them. So in addition to putting all of the non-zero coefficients in any row close together, we end up mapping any two elements of the same block to similar starting positions. So their non-zero coefficients will start in a similar place. And what this lets you do is for the WebPKI example, you have you need a different false positive suppression rate in each block, and so you need a different shape. You need like a different number of zeros on the right-hand side of this equation, this purple region that I've drawn here. And so if you have all of the rows from the same block getting mapped, if I have all of the documents from the same block getting mapped to similar rows, then your solution vector has this little staircase-shaped region of entries that you just don't care about, and you can just skip the encoding of those. Okay, so that's the club card data structure. It's a two-level cascade of these stitched ribbon filters with additional intrinsic metadata describing the domain and a partition. And there's also a secondary encoding mechanism that makes sure that the system is always solvable, mostly as a performance improvement for generation time. All that's available as a Rust library, which you can use to make generic club cards. And then we have the instantiation for CR Lite as well. Like I said, this paper will be at SMP and up on ePrint soon. Thanks.
We have 2 minutes for questions.
Thank you for the talk. I was wondering, in the original CRL Lite paper, I remember they have this section about trying to get rid of the audit log by doing some form of aggregate signature with CAs. I was wondering if Mozilla, you had any interaction with CAs that would be interested in doing this?
We don't currently have that set up. I think there are a lot of different opportunities for removing the trust on Mozilla here. It would be nice if maybe CT logs could check that we've properly encoded everything. How about the known certificates? Also CA is checking that we've encoded the revocations correctly. All of the data is publicly available for each filter that we publish. So this is in principle possible to do today, but we still need some mechanism to actually get signatures on documents and make them publicly available.
Thank you.
You said that you withdrew the CR Lite because you're getting false positives. if it was working as described, would those false positives, would you not be able to remove them? So why did you have to remove it?
Sorry, I'm having trouble hearing the microphone.
So I was asking about the CR light and the fact that you had to withdraw it from service because you were getting false positives.
Mhm.
If it was working as described, you should have been able to negate those false positives in the bloom filter cascade. Why didn't that work?
Well, we were able to get the system working without false positives using bloom filter cascades. The issue there was just purely about the metadata that we were publishing about which certificates had been seen by the aggregator. So we did get it working. The reason that we couldn't ship that version was because of the size of the artifacts and what it was going to cost us to serve those.
Okay, thank you.